All right, it has been a while since I've made a full video. The problem is that I'll come home from work, I'll do some testing, I'll get the answer or it won't work or whatever it might be, and then I just forgot to record it, and then I'll go to bed. So definitely making it a intentional time to record some of these tests, and for that I actually wanted to show you this, what I've been working on. So this is a T-bar. It goes directly on top. One thing that I did find was that you could take a diaphragm and put it on either side of these and it'll vibrate just the same as if it was one. So one thing that I am working on is putting two, as you can see right here, these are two of the coils that have been linked together. I don't know if you can see that, they're linked in parallel. And so those would go on either end of the T-bar to potentially get more current at a half voltage. So parallel versus in series. If I were to connect those coils in series, it would be twice as much voltage at half the current, and vice versa if it was in parallel. So, but what I wanted to show you was this. This is something that I've been working on for a while. I had to get this custom made, and open it up really quickly, then we'll reassemble it afterwards. Got the actual engine, or one of the engines in the way. So this is a 3D printed, you can get it closer, metal 3D printed Wells turbine. This is made out of stainless steel. And what I've got here is a ceramic bearing. I chose ceramic because it has the least amount of resistance. As you can see, it's just still spinning, right? So I wanted to give it the best opportunity to work possible. I have not tried this out yet, so this is something that I'm trying to do now. I'm gonna make the videos during the actual tests so that I don't just try it, find out, and then move on with the next thing. So the way that this works, right, I've got the adaptions. They basically just fit on the end of any kind of tri-clamp fitting, and then I'm going to clamp them in space, and this is going to hold it inside to freely spin on one side of our tri-clamp. So I'm put it all back in. Give me a second to reconstruct this. While I'm doing this, I'm talking about one of my shorts over the week, or I guess a couple weeks ago now. I was messing with different ways to do the engine without having a ice sheet around, because I've always kind of been working on this idea of like it not having to be vertical. So I put all this work into figuring out the correct potting material and what would work and what wouldn't, and a lot of them did not work. Most of the time it ended up in broken glass or whatever it might be. And then it occurred to me, after I'd spent a lot of time working on it, that I could just get an actual covered top here, right? So this right now, this is considered an ice sheath. And the other one's called a water jacket. And a water jacket, you can turn upside down, and water's gonna come out and just pumps in and pumps out. I have an example that I can show you in this video as well. So kind of funny, over-engineering it, overthinking it. The potting material was kind of a good idea, but the problem is you get so high in temperature as well as pressure inside the engine that it just becomes too much for really anything to handle. So now that everything is constructed, you might be able to see the blades in there, see that? And it can freely spin pretty well. It's not perfect, it is 3D printed, but if I can get some good air travel in here, maybe we'll see if a Wells turbine will work for this. I saw a cool video on YouTube by Blade Attila. It's got some pretty cool videos on there. It's actually the reason that I started messing around with thermoacoustic engines and Stirling engines. Problem was the fan that he was using, the Wells turbine, it definitely wasn't hooked up to a Stirling engine, right? It looked like it was a speaker. So the amount of power that was coming out of it would be hard to represent with something like this. I could be wrong, but at least from what I saw, maybe you can go find the video yourself, tell me if I'm wrong. But it didn't look like it was an actual working Stirling engine. It looked like it was just a speaker pumping air. And so at that point, right, if I pumped enough air through any speaker, I'm sure I could get something to spin. So the real question is, can I get it to spin off of a thermoacoustic? We're gonna find out. So let me see if I can get this thing start making some noise. Now I'm going to cover it up because it just tends to make noise quicker. You have a little bit of a vacuum. I can feel the pressure waves on my hand. It's bizarre. It's almost, it's like it sucks in and then it doesn't, and then it sucks, it pushes and sucks. And it's bizarre. All right, we're officially making noise. I'm gonna get a little bit hotter. I'm gonna turn it off and see if you can hear it. I don't know if you can hear that, but. Normally I have, looking for a specific piece of tri-clamp that I must have misplaced. I have a cone piece somewhere that makes it a little bit easier to hear, but I can't find it right now. Let's get a little bit hotter and then we'll put the turbine on there and see what happens. Pitch change just a little bit. I'm gonna clamp it on there. Just a generic tri-clamp. Probably don't need to, but I want to make sure I'm not losing any pressure. I don't see the shaft spinning, so not very optimistic about it. Really can't. I guess you can maybe see some blades in there. Let's give it a push. It's getting loud, but we're not getting any movement from our fan. I can feel it on the ends. So one of the reasons that I made it this way with such a long shaft was so that we could move the actual turbine throughout the duration or length of the thing. So let's see if we can move it as far to one side as possible. So I've got it just outside the edge. I'm gonna go ahead and tighten it, reapply. Sounds like we're gonna have to reheat it. I'll rotate it towards you guys. If you can see it, you really can't see it very well. But it's right here on the edge. If I reach in, I can touch it. So let's see if we can get it to move. Yeah, so I don't think it's gonna work. But this is the kind of test that I would do by myself, basically, right? And I'd be like, oh, if it works, I'm gonna make a YouTube video, and then I would forget to make the YouTube video when it didn't work. It does have a pretty good spin, though. Let me try one more time. Rotate it this way. Alright, well, there's more testing that I can do with this. One thing that I almost never break out anymore is the big boy, the giant Stirling engine, just because it's so big, and I am obviously doing this on a small table, so it can be difficult to use that one. But what I can do, and I will work on, is or modifying this so that it will fit. Well, you know what, I wonder if I can do that right now. I think I can do that right now. So if I put this way, then I need to put this in first. Let's see, now it'll hang. Okay. All right, so let's try without the T-bar. It's not hot at all, that's good. I'm gonna drop this in here. First I'm gonna tighten it up a little bit. Tighten it up a lot more. We'll do it right above. All right, well, no promises. This is an unscheduled test. I guess if we see this shaft moving crazily about, then we'll know that it's at least being affected in some way. Right now it's free floating inside. Let's see if we can get it to make some noise again. Okay. I think that even if this did work, the long shaft is not helping me. So I will just find a shorter shaft, or I'll cut this one, and we'll see if we can get it to work again. If you would like this file, or how I made this, and you want to make it in stainless steel as well, I can send you that file. I'm gonna go ahead and take this apart. The other thing that I wanted to show, oh, there, I have to turn this off. is part of the new year. I've been working on two things, and that is my supply chain, right? So things that I always use. I have good news. The diaphragms, which by the way, I have tried a million times to do pistons. And I want you to believe me, so I'm going to show you all the different attempts. And yes, this is pink. It's because I made my fiance some pink things out of 3D printed. But these are piston models, right? As I went to the same vendor, and I made this. This is a piston that fits inside of a sight glass that fits for a triclamp, right? So it would go inside of this cage. This goes inside there. Basically, this piston is made out of glass and nylon. Super smooth movement inside. It was awesome. I even tried this over here. If you guys have ever been to or heard of the vendor Airpot, this is a graphite piston inside of a glass tube. None of these things worked, unfortunately. So this fits just perfectly inside here. It did move just a little tiny bit, but you don't get the power that you need in order to move a piston with acoustics. And that's because, again, this is not a Stirling engine. This is the Thermoacoustic engine. So we're taking acoustic power and we're converting acoustic power into electrical power. And the way that you can do that is with a diaphragm. And the reason the diaphragm works so well is because the inherent frequency that a diaphragm wants to move matches the frequency of the actual Stirling engine, and then you get this awesome oscillation. An oscillation of the magnet going in and out of the coil is what's going to generate your electricity. So the larger your magnet and the more separation from magnet to coil. One person had an interesting comment about how this gap right here is too much, and something or other. Basically that gap is the size of your magnet. And because the oscillation goes into the engine as well as out of the engine, it's there on purpose, right? Like, you want your magnet to completely exit the field of the coil and then go back into the coil to create your maximum amount of power. What I did want to tell you before I got on a tangent there is that I have secured this year a brand new vendor for silicone diaphragms, which is awesome. They're so much cheaper, which means I can sell them for cheaper. And I actually have a really good supply chain for those. And one thing that I can tell you is different, and that is a vacuum sealed bag, and they're being kept in the vacuum seal so they'll be fresher for longer. These ones are clearer than previous ones I've used before. They're stronger, right? And they're just all around better, honestly. These are straight from the manufacturer, which is great. So I have a ton of these, which I'm gonna be selling both on my website and on my Etsy. If you haven't seen my Etsy, some people prefer to buy through Etsy instead of an actual website. It's up to you. But the other thing that I'm working on is, first of all, trying to make the actual engine is cheaper, right? Everyone thinks they're cool, right? But no one wants to spend the money, and I understand that it's expensive. And I'm trying my best to make this as cheap as possible. I think that I potentially over-engineered this because it's who I am, and it made it a lot of fun for me. It's a cool project. So what I have is this. So I have a brand new supplier for the stack that I use, right? So finally I've gotten to a point where the stack is available. Before it was like a random, maybe I can get a bunch of these, maybe I can't. I have an actual supply for these. Now, I think I have like 500 or something like that now. And I can definitely get more, but these are also available for sale. This is the stack that actually produces the thermoacoustic action. It's 5.9 inches. It goes in here, you heat the bottom, and then you can get thermoacoustic pressure from the top. Now, if you're gonna make one of these yourself, I would suggest that you stick with the design that I have here. So you'll have basically 3 parts. So an 18-inch engine, you've got basically a 6-inch stack, you've got a 6-inch base, and you've got a 6-inch top. Now that is all basically designed with a stupid amount of equations to get the correct frequency in order to draw the power that's going to come out of a stack like this. Now you could get your own and you could cut it in half, or you could get 2 and combine them, or whatever it is you want to do, but if you want it to work just out of the box, that's how it's designed. One thing that you can do, and I did make a video of this with a much shorter version, this bottom piece can be shorter. I have a 2-inch version that I've used before. Originally, when I was making this, it was made for campfires, right? So you wouldn't want a 2-inch one to begin with, because it would just cook the entire thing, and then you're not gonna have any kind of temperature differential. But if you're just like me and you're playing with it on your desk, then maybe you want to go to a shorter distance. I still don't, even the ones that I work on here, because as I'm heating the bottom, and if it was 2 inches from my cooling area, then the cooling area would get super hot as well, right? So to each their own, but I'm going to be putting both of these on a website for sale. I'm not sure how much this one's going to be yet, but they are not terribly expensive. Really, the expensive part of the engine is just the stainless steel and getting it custom made all in one piece. So I will be working on some kind of cheaper design, maybe half of the engine. One thing that people run into when they're making these types of things, or at least when I did when I first started, was I didn't have the ability to weld. So getting a tri-clamp pipe that's 2 inches that has one side welded was really difficult to do, right? Especially when I don't have the resources. So maybe I'll just start selling, 6 or 8 inch pipes, maybe like a water jacket and one side welded closed. Make it easier for you guys. So definitely comments below if you want to talk about what I did here. I will try again with my Wells turbine. I also have another one that I printed 2. I don't know where the other one is. My workstation gets pretty crazy sometimes. But yeah, thanks for watching.